So can you confirm that screen is visible? Online people?
Yes, sir.
Okay. So we were looking at RSA crypto system, right? And the RSA crypto system. Uh, Now I have to talk about certain attacks, how attacks are possible. So as you know that if we can factor n, right, then so that means if you know the primes p and q, in the construction, right, then we know how to solve it, right? Or if we know somehow the value of n and phi n, that Euler function, right? That means the product of p minus 1, q minus 1, then also we can check the system. So the thing is that we can divide the whole attack into different parts. So the first one is we can try random integers to check if they are prime or not, right? And then you compute the product kind of thing, right? So the first question that one can ask is primality testing. Okay, so what are the algorithms? How do we find that if n is an input as an integer, we know that it is a prime or not, right? So primality testing, the polynomial time algorithm was discovered by Neeraj Kayal, Nitin Saxena, and Mahendra Agrawal in 2002. Before that, many algorithms are there, especially randomized algorithm. So randomized algorithms, you try, different times, run the algorithm with certain probability, right? Then with certain probability whether it is correct or not correct and so on. I think these randomized algorithms are basically motivated by casino. So I think, as you know, we talked about earlier Las Vegas algorithm, right? Why the name is Las Vegas algorithm? Because Las Vegas casino is the motivation for it. So today I am going to look at two popular algorithms known as Monte Carlo. So Monte Carlo algorithm. So Monte Carlo algorithm is also a randomized algorithm. Monte Carlo is a place in Italy, which is again a casino. Okay, so all this casino business can be handled with algorithms, right? So those motivations are here to determine. So we need to see that primality testing algorithms, right? Primality testing means if n is an integer, I want to check whether it is prime or not. So we are going to talk about two popular algorithms known as randomized polynomial time Monte Carlo. Okay, randomized polynomial time Monte Carlo algorithm. There are two of them which I am going to talk about. Solvay Stenson algorithm, and the other one is Miller. I'm only going to talk about these two. Of course, there are many others, but you should know some of them at least. What are the approach, and certainly one would like to look at because the algorithm by Neeraj Kayal, Nitin Saxena, and Maninder Agrawal is beautiful. only 6-page paper, and that depends on one identity, the whole thing. Anyway, so these algorithms are fast, first of all. Okay, fast means polynomial time, right? That is fine. But they may claim that n is prime when it is not. So they can give incorrect answer as well. But we can run the algorithm several times to reduce the error probability below certain threshold. Okay, so that is the key idea. Time is coming again today, but anyway. So these algorithms may give you incorrect answer as well, right? So we want to run it enough number of times, make sure that the probability of error is below certain threshold. So the question is, how many times should you run the algorithm? How many random integers? Will need to be tested? Some problem actually in this pen, you know. Until we find one that is prime. I can do some analysis on this. There is a function known as, I don't know if you have heard about this function, pi of n. Pi of n is a function, the number of primes less than or equal to n. How many primes are there? Right? Okay. You might be knowing, if you know number theory, that this answer was earlier given by Gauss. Okay, now it is known as prime number theorem. Pi n, and he guessed this by looking at certain appendix, you know, he was looking at some data and he predicted that this value will be n divided by log n. Number of primes less than or equal to n. How many primes will be there? So number of primes less than or equal to n. Okay. This is known as prime number theorem. So using this prime number theorem, if an integer p is chosen at random between 1 and n, then the probability that it is prime is about 1 over log n. if a number p is chosen between 1 and n, and the probability that it is prime is about 1 over log n. So, okay, so this is coming from this prime number. So essentially, what does that mean? I can compute the data. If we are looking at 2048 bit, so basically when P and Q are primes of length 1024 bits. So one can ask, if P and Q are primes of length 1024 bits, right? That means the product is of size 2048 bits, right? So a random one zero two four bit number integer will be prime with probability approximately 1 over log of 1024, which is equivalent to something around 1 over 710. That means on average, given 710 random 1024 bit integers, P, one of them will be prime. Okay. So you run it 710 times, so on average, given 710 random bit, there will be prime anyway. I can mention that. Integers P. So these probabilistic stuff is pretty interesting. So now I am going to give you definition of Monte Carlo algorithm. So first of all, I will talk about a decision problem. Is a problem in which a question is to be answered yes or no. So decision problem is a problem in which question that needs to be answered is either yes or no. Okay. So a yes biased Monte Carlo algo is a randomized algo for a decision problem in which yes answer is always correct, but a no answer may be incorrect. So yes-based Monte Carlo algorithm is a randomized algorithm for a decision problem where in which yes answer is always correct, no problem. That's why yes biased, okay, it's more biased towards yes. But no answer may be incorrect. When it gives no answer, it may be incorrect, okay? More biased towards yes. Similarly, you can define what is so this. I can say that yes biased Monte Carlo. You can define no biased Monte Carlo, which is more biased towards no. Okay, more biased towards no. So yes biased Monte Carlo has error probability epsilon if for any instance in which the answer is yes, the algo will give the incorrect basically answer no with probability most epsilon. So a yes biased Monte Carlo algorithm has error probability epsilon if for any instance in which the answer is yes, the algorithm will give the incorrect answer no with probability at most epsilon. Okay. These are some basic definitions or jargons, I would say. So there is a difference between Las Vegas algorithm and Monte Carlo algorithm. I can just put a remark here. Las Vegas algorithm is known as dual to this, In the Las Vegas algo, so Las Vegas algo may not give an answer. Means there may be failures, but any answer it gives is correct. That is Las Vegas algorithm. It may be failure, but if it gives an answer, it is correct. Whereas in Monte Carlo, always gives an answer. But the answer may be incorrect. Okay, so this is the difference. Both are kind of dual to each other. A Las Vegas algorithm, so Las Vegas algorithm may be a failure, means sometime it may not give an answer. But if it gives whatever answer it gives, it is the correct answer. In Monte Carlo, always gives an answer, but the answer may be incorrect. Okay, that is the key difference between. Now I can define composite problem. A positive integer n greater than or equal to 2. Question is n composite? This is our decision problem. Answer is either yes or no. Okay, so now I'm going to define SSLGO, which is a Monte Carlo algorithm. So this is a yes biased Monte Carlo algorithm. Okay. For composites. With error probability half. There is some problem. I need to fix this, writing. So this Solovay-Stenson algorithm is a yes bias Monte Carlo algorithm for composites, for our decision problem composites with error probability half. Okay. So let me describe this algorithm. Before that, I think I should mention one fact. Suppose n is greater than 1 and it's odd integer. If n is prime, we know that we saw that this is the Jacobi symbol, right? And one fact that I would like to mention, this is 0 if and only if GCD of A and N is greater than 1. Therefore, if 1 is less than or equal to A less than or equal to N minus 1 and Jacobi symbol is 0, then N must be composite. So 1 lies between A and N minus 1 and this Jacobi symbol A by N is 0, then N must be composite. Input is an integer N, this algorithm. Choose a random integer A such that 1 is less than or equal to A less than or equal to N minus 1. Compute the Jacobi symbol A by N and assign it to value X. If X is 0, then return N is composite. Right? Means it is not a prime if X is 0. Then you compute the other part, A raised to power N minus 1 by 2 mod n. If x turns out to be same thing as y, mod n, then you know n is a prime number, right? Then return n is prime. Else return n is composite. So this algorithm, as you can see that from the previous fact, n was prime if and only if this Jacobi symbol is equal to a raised to power n minus 1 by 2, right? So from that, we decompose it in two parts. So the key thing is that we are choosing the random number a randomly between 1 and n minus 1, right? So you compute this Jacobi symbol, assign it to x. If it is 0, then return n is composite, right? You compute a raised to power n minus 1 by 2 mod n, assign it to y. If both are same, then it is prime. Okay. Otherwise, composite number. So this is the thing. So the randomness comes from choosing that randomly choosing number a, right? We are trying every time. So you have to run it enough number of times. So now a couple of things about this algorithm. The first, we can talk about the complexity. I think, what is the complexity of computing this thing, right? Jacobi symbol. If you remember from the previous class, n is, if you write n as a product, then we know how to expand Jacobi symbol in terms of Legendre symbol, because Legendre symbol, there is a by p. At the bottom, there is a denominator, there is a prime, right? So those kind of expansions we can do. So if we apply that kind of technique, it looks like a difficult thing to compute. But there are certain shortcuts, or I would say certain properties of Jacobi symbol through which you can compute this quantity Jacobi symbol in polynomial time. So let me mention some of these properties. So overall, the complexity of this algorithm is log of n whole cube, which is a polynomial in log n. Okay. So so let me do some analysis for this. Properties of Jacobi symbol. If n is positive, odd integer, and it turns out that m1 is congruent to m2 mod n, then m1 by n is same thing as m2 by n. This is a very beautiful property. So if two numbers are same, congruent to mod n, then Jacobi symbol m1 by n is same thing as m2 by n. Of course, all these things requires a proof, which I am leaving. I am not doing the proofs here, but if you want, you can do some elementary calculations from number theory to prove it. Anyway, that's property number 1. Property number 2. N is a positive odd integer, then 2 by n is equal to 1 if n is congruent to plus minus 1 mod 8, minus 1 if n is congruent to plus minus 3 mod 8, plus minus 1. This will always create a problem anyway. Okay, so this is property number 2. So we will see actually when we compute the Jacobi symbol. I will show you an example. we look at numerator, denominator kind of thing. So we try to make numerator less than the denominator all the time using the properties. And then we apply this formula to compute the value to be 1 or minus 1. Because if n is congruent to plus minus 1 mod 8, the value is 1. If n is congruent to plus minus 3 mod 8, the value is minus 1, right? So let me. Third property. Again, n is a positive odd integer. Then product m1, m2 divided by n, the same thing as m1 by n, m2 by n. In particular, we have if m is equal to power of 2 times t, then m by n is equal to 2 by n is for k by n. This is also quite useful. So if m is here 2 raised for k into t, so we are applying that formula itself, 2 raised for k times t by n, and then this is actually product of all the individual 2 by n into 2 by n up to 3 times. Property number 4, m and n are positive odd integers. M by n. This is a very useful thing and the starting point. First, we apply this formula. If m is same thing as n is same thing as 3 mod 4. So this is what we are going to use. You can see that, normally we switch either n by n or, in fact, positive n by n or minus n by n. M by n is switching, places, right? These are the 4 properties. Let me show you one example how these 4 things are applied. Example 7411 divided by 9283. 7411 divided by 9283. By property 4, this will be minus of 9283 divided by 7411. By property 4. This is a big problem actually anyway. So you see that numerator was less than denominator. So we actually took numerator on the top, denominator on the top, and numerator, switch the places. And now we compute, this is equal to minus 1872 divided by 7411, property 1, using property 1. Then we apply property 3, we actually factor this quantity is 2 divided by 7411 raised to power 4, 117 divided by 7411 by property 3. And this is equal to, so this quantity will be, plus 1, right? So the whole thing left is minus 117 divided by 7411 by property 2. We again switch This is minus 7411 divided by 117 by property 4. This is minus 40 divided by 117 by property 1. So minus 40 divided by 117. So minus 40 divided by 117 is equal to minus 2 by 117 whole cube, 5 divided by 117 by property 3. So this quantity will be 5117 by property 2. Again, this is simplify 2 by 5 by property 1. Oh, sorry. 5 is, this is nothing but 117 divided by 5 by property 4 is equal to 2 by 5 by property 1 equal to minus 1 property 2. So the overall value is minus 1. Of course, this will come when you do some practice of applying the things, right? Know the properties, then you can actually use those things. So what is the complexity of? So we are doing this actually in this all these 4 properties. So in this reduction, what we are doing modular reduction, right? Modular reduction, and we are factoring out power of 2. Because the power of 2 is there, right? Now the power of 2 kind of thing is basically not contributing much in the complexity, because that is just counting number of trailing zeros. So it's kind of constant thing. What is left is there are two operations. Modular reduction I'm just saying that I'm putting the Jacobi symbol this. There are two operations, modular reduction and factoring out power of 2. This is a constant term, number of trailing zeros if you count. So this whole thing will be less than order of log n. I mean, so these many modular reductions are performed, order of log n. And each of these modular reduction can be done in order of log of n square. I'm not proving any of these things, but total complexity turns out to be order of log of n whole cube. And if you do some more analysis, this can be shown to as better as log of n whole square as well. There are two things. Okay, so these many modular reductions we are doing. Each modular reduction can be done with a complexity of order of log of n whole square. So the whole thing is order of log of n. Okay. Second portion is giving you a constant thing. One can actually show that, just mention rather than doing anything else, but I would like to answer this question. Suppose we have generated a number n, a random number. Okay, and tested it for primality. Okay, using SSA algorithm, which I described. If we run algorithm m times, what is the confidence? What is our confidence? That n is prime. So we generate a random number n, and we are testing it for we tested it for primality using SSA algorithm. Okay, so we run algorithm m times. What is our confidence that n is a prime? That is a question. I'm giving you answer without much proof, but I think I have written some notes which you can look at it. Probability that such an integer n is prime is 1 minus 2 is for minus n. All these things are a bit advanced, right? So many things, proofs, but actually there has been a lot of literature, a lot of papers on primality testing. But if you see the beautiful proof of, I will share you with the paper what Neeraj, Nitin Kayal and Neeraj and Nitin and Maninder Agarwal has done. That's beautiful paper, very small, you know. But these algorithms are quite often used, so that's why, you know, we need to at least mention that you should know these things, you know. Okay, so now I can mention the second algorithm. Just mention it probably. I'll not go into details, too many details, but this is also Monte Carlo algorithm. So it's a randomized algorithm. Miller driving. Input is n. Write down n minus 1 as 2 raised power k into m. Here m is odd. Consider a random integer a 1 less than equal to a less than equal to n minus 1. Consider a random integer a between 1 and n minus 1. Compute a raised to power m. Assign it b mod n. Right? Compute a raised to power m. If b is congruent to 1 mod n, then you remember, you know, and n is prime in this case, you know. N is prime. Then we run a for loop 0 k minus 1. Do the following thing. If b is congruent to minus 1 mod n, then return n is prime. Else we compute power of B power, right, and mod n, assign it to B. Return n is composite. So this is the algorithm. So we are using this fact, that a raised power m is congruent to 1 mod n, then n is prime, right? If you remember that result, Again, so randomization comes because we choose the random integer a between 1 and n minus 1. We can do what? We can do the complexity analysis. We can do the probabilistic analysis of this algorithm. So without boring you much, I can just mention the result, right? So this complexity is also order of log of n cube. Okay, same complexity is there. That error probability is less than 1/4. Complexity is order of log of n whole cube. So this is also, I just want to mention this result, that Miller-Rabin algorithm for composites is a yes biased Monte Carlo algorithm. So if you know this much, of course there is a proof, but I'm skipping the proof right now. I have written in the notes, or you can read in the book also, the proof of this fact that Miller-Rabin algorithm is for composite is a yes biased Monte Carlo algorithm. No, I just gave you the definition of yes biased, more towards yes. Okay, I think that's all for today. So probably next class I am going to talk about factorization, 1 or 2 algorithms for factorization, and then so basically then I'll finally talk briefly about the attacks. We can finish. How many lectures are left actually? 6 or 7 or 8? Huh? 8, right? So yeah, okay. Because the next chapter will take 6 lectures at least, So I just wanted to do digital signatures as well because that is also a basic thing, but let us see how much time we have. So that's why I'm skipping some proofs, know the basic things at least. Okay, so that's all for today. See you in the next class.